and welcome to Act 3 of FutureNet. This is Evolving the Physical. How far will it go? A discussion about what the trade-offs are and what this transition is between software and physical networking. The progression between specialized silicon, high-performance hardware, and software implementations of all of the networking functions that are necessary to connect us to the outside world. We have with us today a panel of 5 experts to discuss the topic and explore what it means and what we can expect and what organizations should be planning for in terms of expectations about where and how they'll implement capabilities, how they'll deal with concerns about capacity, and how they'll move forward. We've got a whole set of folks, both from service provider and networking vendor environments. We've got Yiqun Kai, a VP of the Alibaba Group, Ken Duda, the CTO of Arista, Ofer, a fellow with Cisco Systems, Yu Li, the VP of Architecture, Network, and Communications Engineering with Comcast, and Nick McKeown, a professor at Stanford University. Welcome to you all. Would you each introduce yourselves and give us a quick take on what your thoughts are about this shift? So, Yiqun, why don't we start with you?
Sure, great. Thank you, Eric. I'm very glad to be here. So my name is Yiqun, and I'm with Alibaba Group. And today, I want to speak as a cloud operator, bringing a perspective of someone who helped running very, very hyperscale data center networks. I think today, in a cloud computing environment, scale is still a problem to be solved. I mean, it still remains a very, very interesting problem to be solved. But in the meantime, I think scale also brings a lot of very, very interesting things to the table. In essence, scale requires speciality. Scale requires and can afford speciality. In the meantime, scale also brings competitive advantages. So I want to use an example. For example, in a startup of less than a dozen people, one of the software engineers may end up doing the work of IT. One of the system software engineers may end up learning the craft of writing front-end or app softwares. But in a company with over 10,000 engineers, I'll likely have a dedicated IT group working on tools specifically purposed to improve efficiency, and dedicated UED people to design interfaces. The reason I'm using this example is to show that in a very, very hyperscale data centers, we will need specialized hardware. And we will need dedicated software tools and paradigms in order to take advantage of those specialized hardware for us to fully leverage the scale and then increase our competitive advantage. So yes, we would very much like to see the advancement of silicon and the programming networking software hardware going forward. So yes, I'm very much interested in what other experts want to say. Thank you.
Ken, why don't we go over to you?
Thanks, Eric. My name is Ken Duda with Arista Networks. What we're seeing going on in the industry is a really exciting trend of just increasing integration, increasing capabilities in network silicon. Modern network silicon is capable of doing all of the packet manipulations and all of the table lookups that are required for large-scale service provider routing, all the complex MPLS features, at the same time doing all the overlay features, all the security features, all the telemetry related, all in one piece of silicon. And so what we're seeing is a greater integration of features into devices. So a top-of-rack data center switch is capable of overlays with EVPN. It's capable of running a full MPLS stack. It's capable of all the network packet broker functions that you associate with telemetry networks, with network analysis and network detection and response. This integration gives our customers a lot more flexibility, doing L2, L3, or even L1 switching, along with features like timestamping, packet truncation, deduplication, all in one box. And I think that's going to continue as we see the feature set continue to increase in merchant silicon, along with the availability of the cloud to enable us to provide services to our customers, managing the network, providing visibility, and security features as well. So we're seeing a lot of drive from the silicon to improve the physical network.
Ofer.
Thank you, Eric. I'm Ofer. I'm a fellow in Cisco, and I focus on silicon, So my view is really from the very bottom. I think that, as Ken said, we see greater and greater integration in silicon. The process technology and the technology we have today allows us to do some incredible things that we could never really dream of in the past. However, I think, as many of you probably already heard, we are running into quite a big challenge, how to continue to meet the demand for improved performance, especially related to consumption. And I think that that's going to force us to think really hard about specialized, potentially silicon, in order to continue to drive the performance and continue to find ways of improving things. So while I agree that we're going to see greater integration, I think at the same time, again, related to the discussion that we have today here, we will see some interesting opportunities around specialized silicon. And of course, I think there will be quite a challenge around that, how to make that work, because I think that you can realize specialized silicon presents a challenge how to maintain agility and how to keep things simple. I think that would be an interesting challenge, and I believe we're going to discuss some of the points in a moment around that. So thank you very much.
You.
Hey, thank you, Eric. It's Yuri here from Comcast. I think from the market trend perspective, we're definitely seeing a lot more specialization coming from the silicon side and also from the OS side, and that kind of like clean separation is happening in the industry. And then we do see that as a great opportunity, especially when you're talking about technology evolution. At the same time, we're also seeing some convergence at the other end from the skill set perspective. So we're seeing the NOS OS now is getting like a lot more similar to the server OS. I mean, people used to develop, and that we see the opportunity now to unify the skill sets, especially from the operator perspective, how we can leverage the people who already familiar with those tools, and then bring it to the networking. And that is something that, like from the operator perspective, that is really key to us, because we can increase the speed to introduce any services to our customer. At the same time, we can unify the tool set that we will be able to vertically integrate from the application side to the network side. And this didn't happen in the past. Networking and application are always running in two silos, and we see that like opening up. And this is a great opportunity for the industry, and this is also a great opportunity for us to discuss. I mean, this is something that I'm really, really excited. Thank you, Eric.
And Nick.
Hi, my name is Nick McKeown from Stanford, and I think that the last 10 years is, in terms of silicon, has been the decade of domain-specific processors. We've seen specialized processors emerge for machine learning with the TPU, etc., and for graphics before that. And we've seen that the people have started to write their own programs on hardware which is optimized to accept programs for particular types of service. And networking was a little slow to this game. We used to feel that everything had to be fixed function. But as Ken pointed out, the rise in the complexity of the silicon means that it's become increasingly difficult to design and verify that they are correct. So we've seen in the last few years the rise of programmable switching and SmartNIC silicon that gives the owner and operator of the network, or the builder of the equipment, the opportunity to specialize that and also just have the programs that they need and then add their own as they grow and scale their network. Because after all, it's the owner of networks that really understand how to build networks and what they need. So this gives them the choice to determine that for themselves.
Thanks, Nick. An interesting set of opinions that really span the scope of networking approaches and really what we're looking towards in terms of this transition. So I'd like to throw out our first discussion topic, which is how specialized are networking capabilities becoming And what should we expect? Is this something where we're hitting the constraints that general purpose processors can provide, and SmartNICs, distributed processing units, DPUs, are the way that it all winds up? How much dependencies go in each direction? And what's the role of more programmable capabilities like P4 processors that can actually do specialized networking capability in this whole role? And I'll throw that out to whichever one of you wants to dive in first.
Well, I'll go ahead and bite. I feel from the network equipment side, programmability is fundamentally an implementation choice. Programmability is, as Nick said, it can be difficult to verify these complex chips. And perhaps you can get to market sooner if you leave more of it open and then fill in with programming after the chip has been taped out and has been shipped. Where I think there's some confusion in the industry is the extent to which programmability is important for the ability to add features after the fact. And I used to wishfully hope that this was the case. And we saw our opportunity back in 2014 when VXLAN first really arrived within people's consciousness. And we were able to produce the first switch with hardware-accelerated VXLAN, thanks to the programmability in Fulcrum Microsystems' Alta chip. And customers cared exactly zero. The problem was, to adopt something new like VXLAN requires changes at every layer. You've got to have changes in the way you provision, in the way you engineer your network, and what you're doing on the end stations, and how you do network monitoring and debugging and troubleshooting. It just takes time to adopt something like VXLAN. We didn't see large-scale deployment until maybe 2017 at the earliest. That's an entire generation of silicon. And so the take-home lesson of that experience to me was that changes to the way the physical network work are difficult enough that you have the time to plan them out with operators, integrate them in the next generation of silicon, even if you don't have the programmability features required to implement them on current silicon. There may be some use cases in the cloud where there's some very advanced engineers wanting to do some experimental work where programmability in the silicon makes a big difference. But for the typical enterprise consumer, large-scale enterprise data center, I don't see programmability in itself delivering value to the customer. It's really just an implementation choice. So that's nice and controversial. I'll put that out there and let Nick jump all over me.
So I think the VXLAN makes for a great example, actually, and I would say that it's a perfect example of the opposite of what you just said. And that is that, so VXLAN was first designed by Cisco and VMware back in 2010. And you're right, the first silicon didn't show up until 2014, even though there was quite a lot of demand for it. And in the meantime, what people had to do was to find other ways to sort of force fit what they needed to do out of old VLAN headers and other headers that they had available to them. Had it been available at the time that it was first standardized, then I think you would have seen a much more rapid deployment. And why wasn't it available at that time? Because whereas, you and your team can develop software in a few months for a feature like that and have it ready for deployment, it took 4 years for the silicon to have that feature in it, even though it was in one of the most highly invested, most highly competitive parts of our industry. So one of the other things that happened as a consequence of more programmable silicon, and I don't just mean from Barefoot where I was part of that, we've since seen that arise in many other places as well. What happened as a consequence of this, the features that were not really feasible to implement before by the owner of the network or from the equipment vendor started to appear. And I think telemetry, as you mentioned, is one of the big examples of this. I've had the opportunity to witness the deployments of programmable switches into a number of different cloud providers. And it's kind of interesting that every one of them does telemetry and measurement in a slightly different way because of the specific needs that they have for in their environment. Similarly, they've started to deploy congestion control in their own way. As I'm sure from following the literature, you've seen that most of the cloud service providers have now deployed their own specialized congestion control mechanisms. Many of those incorporate changes that they've introduced into the switches and the NICs in the network. This was made possible because of the programmable infrastructure. So I think actually it's been a time when we've seen the testing the waters, putting the toe in the water for that expansion of capability. And I actually think over the next few years, rather than networks becoming simpler and all around standardization of protocols, we will see more and more experimentation as they're sort of unleashed from this stranglehold of fixed silicon they've had in the past.
Eric, maybe I'll jump in and give maybe a perspective a little bit from a silicon designer perspective. And I think Nick also is aware of that. I think that there's always a challenge and there's always a balance between how programmable you make it versus how efficient a particular function is. And I think what happened is that, as we mentioned in the introduction, over the years, as process technology became more and more powerful, it allowed us to do things that we were not able to do earlier, like baking in more programmability into it. There's no doubt that programmability can help a lot. I think the problem with that is that every vendor builds programmability differently, and it becomes enormously difficult and challenging to actually use it effectively. Ken happens to be a superstar engineer, and we go way back, and he has a perspective that yes, I can program anything that comes to me, but the truth of the matter is that for most of us, it's quite difficult to take the full advantage of programmability. I think what ends up happening many times is we build a lot of programmability. In Cisco, I know we build more and more programmability into our silicon. We always build programmability. Now it's everywhere. But this programmability, it's very difficult to make it accessible to, let's call it, third-party engineers. Yes, the big guys, and I think Nick is right here, the big guys, the big MSDC guys, cloud providers, they can afford to spend, the human resources and the time and the expense of doing that. But I think the general population, it's very hard to do it. So I'm not sure that the programmability, when we say programmability, we really think about programmability as CPU, like an Intel CPU or whatever CPU. It's very hard for me to see how we get there in the sense to enable this type of programmability for the type of equipment, the networking equipment that we're talking about. And this, of course, then relates also to SmartNICs and the new the transition to this new architecture. But I will stop here and I'll let other guys comment.
Well, we've got two of the big guys here, and it looked like Yiqun, you were sort of champing at the bit there. What's your thought? Are you able to consume that level of programmability? What's the level of specialization, and what are your thoughts on it?
Yes, actually, in Alibaba, we started deploying network programmable functionalities from back in 2018, I think. We started deploying telemetry-based functionalities that requires network programming. And then after that, we've invested huge amount of resources in network programmable networks, in advanced gateway functions, congestion controls, and so on. So in essence, yes, we've done lots of work in programmable networks. And then we have been running productions supporting, for example, in Alibaba or in single state events for the past 2-3 years. And we have actually primarily P4, and then we've reaped lots of benefits. Now, I want to say why we're doing that, right? Exactly as Ken mentioned earlier. Typically, silicon generations takes about 3 years to complete. And in the early days of the cloud networking, while we are trying to understand exactly what cloud computing is, 3 years was acceptable. Now 3 years is not acceptable. We need much faster turnaround time. So that's just one reason, right? The second reason is, yes, as we all said, because we have scale. We have scale in knowledge and scale in development resource that we can leverage to develop our software to demonstrate our competitiveness, right? Our competitive advantage. But the real or maybe an additional reason once I discussed with Nick some time back is when we don't have the network programming capabilities, we can't really apply the software engineering principles into networking in a very, very complete way. For example, the model, how can I model a behavior of a switch without being able to program it? In a way, I once mentioned to Nick that, I want to be able to have the network programming in a way that I can use software languages to specify the switching behavior. And therefore, the switching behavior can be verified in a distributed fashion, not as an individual box. And then I know exactly what's happening in the network. Once I mentioned, in any large cloud networks, if we call network element as an interface or system or transceivers, right? You have tens of millions, sometimes 100 million of network elements in the network. Today, there's almost no way to model it. If you can't model it, you don't know what's going on, what's going to happen next if something happens. And the only way to solve it is to treat the entire network as a distributed system and using software engineering principles to deal with it. Because today, software engineering principle is the only way we know to design and manage a large distributed systems. So I'm personally a very, very firm believer of network programming capability. Are we there yet? We're probably not there yet to be able to understand network the same as distributed systems, right? And then I mentioned to Nick, I mentioned to other folks, and network programming is very, very important. And then we also need not just how to do it, not just P4 languages and the advancement of P4s. We also need better toolings in general, how to compile it, how to verify the system, how to model it in such a way that we can verify it, we can manage it. And then we can continually writing applications for it. Writing application is just one part of it, in my opinion, right? So yes, I'm a firm believer of it, and I think we have lots of work to do. So that's my perspective. And I'll be happy to share the experience that we have in the past 3-4 years of working in this area.
Another service provider that we've got with us, where do you stand in that spectrum of being able to leverage programmability and being able to do that at the scale that's necessary?
Happy to share. I mean, we're probably on the other end of the spectrum here. So we really appreciate the programmability for the chips. That one is definitely enable us to do quick prototyping and try to test out what we have to do, what we can do in the future. But at the same time, we don't have the same, because we have to strike the balance between the investment and also the programmability. At some time, if let's say you try to customize on your network, this is something that more customized into it's a customized solution. So in this case, it's then now you have to, we are responsible for all the outages. We are responsible for all the operation issues. And depending on the use cases, different operators have different use case. But for us, definitely, this is not something that we see a huge ROI for us to do it. So we are counting on our partners like Arista or Cisco or anybody else to help us to, once we prototype it, then we can share with them, then they can help us for the lifecycle management for the software. Well, so that's why I'm saying that in the end, it's about the balance here. So we definitely like the programmability so that then we will be able to test drive something that we don't have to wait for years to do. But at the same time, this is not something that I think as a service provider, we are ready to invest building armies to try to program our network to do it. At least not at this time until we feel comfortable to do it by ourselves. Because I think one thing we leveraging the vendor to do it is they probably see more than we see because they're serving multiple operators, and they will come up with some best practice that we think we can leverage. And from our perspective, the cost versus the cost versus the efficiency is always in our mindset because we are running a business there, and for us, it's as a service provider doing serving our residential customer. Serving our connectivity customer. We are looking at it is from the core network perspective. The function is pretty standard, and we have to balance the cost because every time you're doing the programmable, you look at the chipset family, even we are talking about very specialized chipset for networking. There's no one chipset fit all because we have to balance the cost, to do a hyper throughput in certain area. But then in the edge, maybe you want to have a more flexible or deep buffer chipset. And in the end, it's all about the economics of running a network. And I think that the programmability definitely has an edge there, but I don't think that every part of the network requires the programmability. And then that's purely from my opinion. Happy to hear like other panels to chime in.
You know, I think that I get a sense of deja vu when we're having this conversation. I can remember when I was a graduate student, there was a debate going on as to whether graphics would ever be programmable, and that something called the GPU that was out in the distant future would ever appear. And there were people that were really arguing that, particularly people who were building graphics, sort of graphics equipment, who were saying, no. We know what the functions are. There really aren't that many of them that you need. You need rendering and you need a few other things. It's probably best done in fixed function silicon. And at the time, there was a lot of skepticism as to whether you could build programmable graphics devices that would have the same power, performance, and area, and therefore cost, as the fixed function devices that they were replacing. And then the GPU arrived and the world changed. And it changed because suddenly everyone said, it's all about software. Who cares what the hardware is? I don't need to think about it anymore. I express a behavior that I want, a rendering behavior or whatever it happens to be. And then I just compile it and I don't have to think about what happens after that. And there was an explosion of innovation in graphics. We wouldn't have Pixar. We wouldn't have many of the things that we see today in gaming if it hadn't been for the GPU and the innovation that it unleashed. Networking has actually been slow to this game. When I say deja vu, I'm actually kind of surprised that we still have this discussion. If you put programmability into the hands of people who build very big systems, they will do shockingly surprising things. Sometimes they'll do stupid things. Sometimes they'll do dangerous things. But most of all, because they are the ones with the most at stake, they will shock you with the cool and beautiful ideas that they bring to the table. Now, networking, as Ofer pointed out, is a discipline where a relatively few number of people are writing the programs. And I think that's absolutely the case. It's nowhere near ready for a sort of a mass audience like Linux or the C programming language is. But we're at a point where folks like with the expertise of Ken and his team, or of the cloud service providers like Yiqun and his team, are in a position to be able to do that because they know what they need in order to differentiate from others. It's all about software.
Definitely. I mean, we align here. Well, I think the things that I try to convey here saying is not every single operators will have to have a team to do the programming. We probably delegate to Ken, to Cisco. I mean, from over, they will do it. And we are not against any programmability. But I'm just saying that like even for the GPU, you may have a lower class GPU that have some limitation, and you have a higher class CPU that you pay more to be like able to trade off like some of the flexibility. So, but I'm saying that here is definitely saying, hey, not every single operator will have a team or army to try to program the network.
Risk of being too agreeable, I'm going to agree with Nick here as well. Nick, I'm completely with you that enabling this experimentation is incredibly valuable. Arista has kept the switch software stack open from day one, so we have programmability at the control plane. We've been focusing here on P4 in the data plane, but control plane, management plane programmability matters as well. And only a very small handful of Arista customers have really taken advantage of that, but they buy a lot of switches. So it's actually worked out really well for us. And I think, to your point, has enabled the kind of innovation and the kind of just being able to bring big new ideas to life. That's just really gratifying to be a part of. So thank you for your contribution in enabling that in the data plane.
I would just add from a practical perspective. I mean, I think we all agree that programmability has a certain cost to it, and it's a great thing, and it adds a lot of value, but it does have a certain cost. So programmability becomes practical when the technology allows us to pay that cost. So the fact that in the past we didn't have it, I'm not sure it was simply because we didn't want it. It was just because it was really, really hard to pay that programmability time. Now, I know that with great architectures, we can squeeze and reduce that tax, but there is physics at the end of the day, and you can't make it, you can't drive it to zero. And what happens and for programmability to be very accessible, you also to make things very homogeneous. You have to make things relatively simple. And simple programmability is even more difficult to build without significant time. So there's a balance here, is what I'm trying to say. And I completely agree. I think Nick's vision is that as we move forward, more and more programmability will become available and accessible. I completely agree with that. It's just that, we need to walk the path, and this is what's happening. And I completely expect that, it will become a bigger part of what's the way we're going to use and the way we're going to build the network.
Oh, that's really, really hard. The modern layer 2-3 switch has more features than you can shake a stick at. And you've got TCAM-based features, you've got exact match features, you've got longest prefix match-based features, you've got all the actions that come out of those lookups and all the ways those actions resolve. And building a sort of a working layer 2-3 pipeline with all those features is a tremendous challenge. And getting that whole feature set to fit inside programmable silicon is not a trivial engineering exercise. And once you've gotten it to fit, then for the customer to because most customers, what we found with programmable silicon is the customers are not really interested in sort of rebuilding the entire forwarding pipeline themselves. They like to kind of insert or overlay their own sort of take on things, their own experiment, their own, I guess to Nick's point, their new congestion control mechanism, for example. They want to recognize one extra bit and do an extra lookup and kind of insert that into the pipeline. It's just really challenging. I don't know if that problem can be solved easily by additional abstractions. I'm interested in Nick's take on that, because fundamentally the whole thing is to map down to the gates and fit. And the abstractions, unfortunately, my experience is they've, at least historically, more gotten in the way. And on the 3D graphics analogy, having used both OpenGL and Direct3D for graphics programming, I found that the abstractions OpenGL actually complicate understanding how to harness the hardware properly, whereas the more sort of direct mapping of Direct3D to hardware primitives actually simplifies taking advantage of the hardware. So I'm not sure if more abstractions are really the answer, but maybe I can delegate this to Nick as well here.
I think the language and the abstraction really matter, and we've seen in all programming sort of programming paradigms that over time languages have evolved and improved as the problem is understood better. And I think graphics is a great example of that, and we see, of course, that in the world of computing. And so, we've seen in 2 generations of P4, and I'm sure there'll be many more generations of it too, and there'll be other languages and there'll be higher level abstractions. And I think that the natural next abstraction is, now that we're seeing devices that are programmable from end to end. Of course, we've always been able to program the endpoint through user space DPDK and then eBPF into the kernel and the host networking stack written in a software language. As we see the SmartNICs that are programmable and have programmable pipelines in them, and the switches, of course, we are for the first time in a situation where we have end-to-end programmability. Everything in that pipeline is programmable. So it's not that one device has become programmable. It is the first time in networking for which the entire pipeline is programmable. Add to that the fact that the control plane has been opened up gradually through open abstractions with APIs. So networks are now programmable top-down and end-to-end. And this is kind of interesting because suddenly you can think of it as the network as a programmable platform for which you can start to introduce new abstractions, new APIs. You can verify across those APIs and abstractions. I think that we'll start lifting networking somewhat out of the dark ages into a time where the software engineering tools and techniques that have been applied to the rest of our industry for many, many years can now be brought to networking for the first time. I think it's actually a very exciting time for networking because of that opening up of what I refer to as deep programmability, everything programmable as a platform.
Well, it sounds like that's the ideal that we're going for, that's somewhere in between, Yiqun's capabilities with the highly skilled approaches, as well as need to actually leverage this and work with this in a practical fashion. Well, we're at time. And I want to thank all of you for your thoughts and insights. Thank the audience for hanging in there with us. And we'll pass on to the next act in FutureNet. Thanks so very much.